One of the main objectives of this chapter is to know how to design a beam in order to not exceed the allowable value of compression and tension for stress. So for example, these are some guidelines that can help you into the design procedure. In case you have an imposed material for your beam, then you should determine first what are the values of the allowable stresses for tension and compression. And then you can use a certain table of properties of the material that will give you the maximum allowable tension and the maximum allowable compression. So sigma max or sigma allowable tension and sigma allowable compression. Then the next step will be to determine, knowing your load, the load acting on your beam, you can draw the shear and bending moment diagrams, and you can determine the maximum, absolute maximum value of your bending moment. Now, as we discussed last time, if you have different values of C1, C2, you should also consider the maximum positive bending moment and the maximum negative bending moment to know which is the critical case. And based on this, we can select the minimum allowable value for S minimum. So you know that for a certain section, you have to select a certain corresponding cross section that will avoid reaching rupture. So S, which represents the modulus of the section, can be designed based on the maximum bending moment and the value of sigma allowable. And once we have all of these informations, then we can design the beam. So we can find the size of the cross section, or also if it's a standard cross section, we can go to Appendix C and do appropriate selection of a modulus of elasticity corresponding to a section modulus that will give us the acceptable design. Now, sometimes we have several choices of standard cross sections. So among the beam section choices which have an acceptable section modulus, which will allow us to not exceed the maximum imposed stresses, we can select the one with the smallest weight per unit length, because the other criteria will be the cost. So whenever you are on the safe side and you have different options to use, you will select the one that is the least expensive, and this will correspond to a smaller weight per unit length. And if you remember, when we introduced Appendix C, we said that they gave us an idea about the depth and the value of weight per unit length, in addition to values of inertia, modulus, etc. So now when we will do the problems, we'll practice again how to select the corresponding section, which will allow us to not exceed the maximum allowable stresses, and at the same time that will reduce the cost. Let us continue now with different problems on this chapter. So here, for example, we have the following beam. The beam is S-shaped 250 times 52. They want us to draw the shear and bending moment diagrams for this beam and to determine the maximum normal stress due to bend. So first, let us look at the type of load acting on the beam. We have a beam subjected to external forces from a pin at A. So at A, we have a X and a Y. You have a roller at D. At D, you have just dy. So the first step will be to get your external reactions. You have that there is no loading along X, so AX is 0. Now, to get AY and dy, all you have to do is to use two equilibrium equations. You can select or two moment equations, or one moment equation, one force equation. So whatever you do, you'll get the same result. If you want to use sum of moments about D, you'll get directly AY. And then if you do sum of Y equals 0, you get the value of dy. And of course, when you calculate external forces, you can replace this distributed load by a concentrated force. Concentrated force will be equal in magnitude to 24 times 2, which is the area. And it should pass by the centroid of the rectangle, so it should be at 1 meter from D. But keep in mind that whenever you do a section, you cannot reduce the load before doing the section. Okay, so we always do we replace a distributed load by a concentrated force after doing the section of interest. So here, for example, when you deal with the section from D to B, you do the cut, then you reduce the remaining part if you want to do the analysis on this part. After you do the cut, you reduce the distributed load, because we already discussed that whenever we compute internal forces, we cannot replace the distributed load by concentrated force before the cut. We can do it after the cut, because it can help us into getting always external reactions. And when we do the cut, internal forces becomes external reactions. Then we can replace the distributed load on the remaining part by a concentrated force. Now, let us use the area method or the section method. So here, again, you can practice with this problem with both methods of section and area. Here in general, what they are doing is they are using the section method. But the area is easier. So when they don't impose on you a method, use the area because it's easier. So to start with, you have already from your calculation of reactions that AY is equal to minus 28. So it's 28 downward. And therefore, as we discussed, since it's a downward force and we are starting to draw the shear from A towards B, from left to right, this will cause a downward jump in the shear. Now, from A to D, there is no change in load. So you have constant shear. At D, you have your roller, and you calculated your roller reaction. Your roller reaction is 76 kilonewton upward. So a concentrated force will cause an upward jump in the shear when I move from left to right. So minus 28 plus 76 will give you a plus 48. And now from D to B, you have omega is 24. And we are considering omega positive downward. And we know that dV by dx is equal to minus omega. So when omega is downward, then V is decreasing. And since omega is constant, V is decreasing in a linear way. So it will decrease linearly. And we should verify that at B, the shear should end by 0. Why? Because at B, we don't have an external reaction or an external force. So the shear will go to 0. We can verify this because the area of this rectangle is equal to 24 times 2 equals to 48. And since W is downward, V will decrease. So delta V is equal to minus this area. And since the value of V was plus 48 at D, after doing minus 48, we go to 0 at point B, which is expected. So this is how to draw the shear diagram using the area method. If you want to use the section method here, we just need to do 2 sections. Why only 2 for shear? Because a couple will not affect shear. Okay, it will affect the bending moment. And of course, it will affect it indirectly through the values of reactions. Whenever you have a couple, the reactions will be affected. But if you look at the shear diagram, you don't see the effect of the couple. You can see it in the moment diagrams, because we'll see together that when you draw the bending moment diagrams, if you are moving from left to right, then a clockwise moment will cause an upward jump in bending moment, and the counterclockwise moment will cause a downward jump. So you will see directly the effect on the bending moment diagram. Now, If you want to use the section method and find an expression of V, you need one expression from A to D, because there is no change in forces from A to D, and another one between D and B because you have the distributed load. So if you want to get for the first section, okay, from A to C, the expression of the shear, then all you have to do is to do a cut. So if you do a cut between A and D, you just have the AY reaction, which is downward. And since you kept the left part, the shear is positive downward. So you write sum of y equals to 0. This will give you that V is equal to minus 28 kilonewton. You can verify this because we already did it using the area method. And to get the expression of the bending moment, okay, your bending moment will here you should pay attention for something. If you want for your shear, as we discussed, the shear is not affected by the couple. So if you find the expression of shear between A and C or between C and D, it will be the same. So if you take a section from 0 to 2 or from 2 to 4, for the shear, nothing will change. But for the moment, it's not the case. So this is why, because for the moment, the couple will affect the equation, then we should do one section before the couple and one section after. So in overall, for the whole beam, to get equation of M, you need 3 regions, one between A and C before the couple, one between C and D, and one between D and B. So in overall, for your beam, you need 3 sections, 1, 2, 3. For sections 1 and 2, you have the same expression of shear because the couple will not affect the shear, and you can verify this. If you do the balance from A to C or from C to D, you get same shear. However, you will get different moment equation because you have the couple, okay? And the only difference is that the couple will add to the bending because it's a clockwise couple. Your bending moment will be added by 64. So if you observe now after we do the equation, we'll just see that the only difference is that you in section C from to D, you add 64 to the value of moment in the first section, to the equation of the moment in the first section. Let us verify this. If I take before point C, then and I want to write the equation of bending moment, I just have sum of moments about this point equals to 0, and then I have plus M and plus 28 times x equals to 0. So the bending moment is minus 28x. You can verify that the derivative of moment will give you the shear. Now from C to D, what will just change is that in addition to the moment of AY, you have the couple, okay? And since we considered that we rejected the right part, the bending moment is positive when it will compress the upper part of the beam. So this is your direction of moment. And this is why when you write your equation, you take plus M plus 28 times this distance, which is x, and minus 64 equals to 0. So then you get that your bending moment in this region is minus 20x plus 64. So what will change at C is that you have a sudden jump in bending moment. And as you can see, a clockwise moment will cause a positive jump when moving from left to right. And after this, the slope will not change because the slope with respect to x will remain the same, while the slope will remain the same because V will not change before and after the couple. Okay. Now, if you don't want to use the section method, you want to use the area method to determine the variation of M from A to D, all you have to do, as I told you, keep in mind, whenever you draw the bending moment diagram, you should look at both the loading and the shear. Because if you just look at the shear, you will not notice that you have on C a couple. However, from the diagram of load, you can see this. So always when you want to draw M, look at the loading to check if there is any couple, to know if there is a jump in bending moment. and then you can use the shear to know how the bending moment is valid. So first, um, let us start between A and C. Between A and C, from the shear diagram, V is negative constant. So because V represents the slope of M, then M will be decreasing in a linear way, and this decrease is equal to this area. This area is 28 times 2. So you have that the bending moment at point C is minus 56. And you can just go in a linear way from 0. We start by 0 because we have at a pin, and we know that for the pin the bending moment is 0 if the pin is at the beginning of whatever is your pin, when you reach the pin or when you reach a roller, bending moment at pin and roller should be equal to 0. Okay, and we have seen together that this apply also for hinge. If you have an internal connection between your beams, the bending moment at the connection is 0 also. So always you can check this, and you can use it as information to draw your diagrams. So because at A we start from a pin, then the bending moment should be 0 here. And also at the roller level at D, the bending moment will be 0. So now, if we consider, if you want, the corresponding, sorry, here at D it's not 0 because D is not at the extremity. It's not at the extremity of your beam. Okay, so when your roller is at the extremity, it should be 0. However, here your roller is in between. Whenever your roller is in between, you can have a bending moment at it that is different than 0. Okay, but for a hinge that is connecting two parts, two beams, at the hinge the bending moment should be 0. Okay, because whenever we have extremities, at extremities, pin or roller or hinge, the bending moment should be 0. But in case we have an external support at the middle, that is, the bending moment can be different than 0 at the start. Okay. However, when you take two parts of beams connected through a hinge, then since you have for each part, when you do each part is in equilibrium if you do the analysis here. Okay, then you consider that this is at the extremity of this part, and then the bending moment here should be equal to 0. So now if we perform our calculations for using the shear diagram to plot the moment diagram, then first we said that from A to C we have decrease in M. Now at C, because you have a clockwise moment, and you can see the clockwise moment from the loading curve. So if you look at the load on your beam, you have a clockwise couple at point C. This will cause an upward jump in the bending moment. So you will go now from minus 56, you add plus 64, then you have 8, a bending moment equal to 8 at this level. And then after this, from C to D, as you can see, the profile will be of same slope, because before C and after C, the shear is not changing. So here the slope phi was equal to minus 28, and it will remain equal to minus 28 here. So just you have the jump at point C, and after this, the profile will continue to be linear decreasing at a slope of 28. Now, to know to which value you will go down, then you just need to compute the area between the shear diagram and X, which is equal also to 2 times 28, which is 56. And since it's below the x-axis, V is negative, so M is decreasing. So I should decrease from A to minus 48, because the value here is equal to 8 minus 56 minus the area limited by v and the x-axis. 8 minus 56 will give you minus 48. So now you determined at this point what is the value of your bending moment, and then you still have the last part. The last part is from D to B. From D to B, you have a linear decrease in velocity. Okay, please keep in mind also a jump in shear will not cause a jump in bending moment. It will cause a sudden change in slope. So before D, the slope was minus 28. Now just at D plus, the slope will be plus 48. So you have a sudden change at D of the slope of the bending moment because of the concentrated force at D. So a concentrated force will cause a jump in V and will cause a variation in slope in M. A concentrated couple will cause a jump in bending moment. Okay, if it's clockwise, then the jump is upward when you move from left to right. And if it's counterclockwise, the jump will be downward. So now from D to B, you have V is linear. So M is a second degree parabola. Okay, so M is second degree. And to know the concavity, you can just look at W, because the second derivative of M is equal to minus W. Okay, so here in this problem, since W is positive, because the positive convention here is downward, so the second derivative of M is negative, so the concavity is downward. And you can verify this from the variation of V. V is decreasing, so the slope is decreasing. So let us draw together M. So first, as we said, at point D, we have sudden change in slope. The slope was minus 28, and now suddenly it's plus 48. And this slope is decreasing, is positive, but decreasing until reaching at the end of the beam a value of 0. So at the end of the beam, the slope of the bending moment is 0. So you have a horizontal tangent line. And then this is your second degree parabola, and you can verify that the concavity is down. Okay. So now you can verify also that I should end by 0 at the end of my beam. At the end of my beam, I should end by 0 because I don't have, as we discussed at extremities, if you don't have a couple or you don't have a fixity, so you just have a roller, a pin, or just you don't have anything, or you have a concentrated force, all of these will not lead to a couple. So in order, whenever you have at the end like a distributed load or a concentrated force or an external reaction as pin or roller, these will not lead to a bending moment at this point. To have a bending moment different than 0 at the extremity, should have or a couple acting on this point, or you should have a fixity, because the fixity reaction can develop a reaction couple. Since we don't have this here, then we can be sure that at the extremity will end up by a bending moment equal to 0. Okay, and then now, once we are done with the bending moment diagram, we can determine what is the maximum positive moment, what is the maximum negative moment. And here you can see the section method corresponding to the last part. So if you want to use the section method for part between D and B, then what you have to do is to do a section as we discussed. You do the section before reducing the distributed load. So you keep the distributed load, you do the section. This is section 3. Since this part is easier to work with, you reject this part. And because you kept the left the right part, then the convention is V should be positive upward to rotate clockwise about the end of the beam, and M is positive clockwise. Okay, so you get this figure. Now you can, to compute V and M, you can reduce the distributed load to a concentrated force. This concentrated force is function of x. Why? Because this section 3 is at any distance x between 4 and 6 from the origin. The origin is A, okay? So since the distance from the section to A is x, then the length of this part of the beam is the total length of the beam, which is 6 minus x. And now we can say that if you want to replace this distributed load on this part by a concentrated force, the concentrated force will be equal to the area of the rectangle, which is 24 times 6 minus x. And after this, you have to calculate the distance from the section to the force. And since it's a rectangle, then the concentrated force should pass by the centroid. The centroid is at the distance over 2. So the distance between the concentrated force replacing the distributed load and the section point is 6 minus x over 2. And now, using the section method, to find V, you do sum of y equals to 0. Sum of y equals to 0 will give you plus V minus this force, which is minus 24 times 6 minus x equals to 0. You can get the expression of shear. And for the bending moment, you do sum of moment about the section point is 0. And then you get, if you consider the counterclockwise as positive, since the bending moment convention is positive to compress the upper part, so you will take it here clockwise. So you put minus m, and you have for the distributed load, which is replaced by a concentrated force. Also, the moment is the moment created about this point is clockwise. So it's minus 24 times 6 minus x, which is the force, times the distance to the point, which is 6 minus x over 2, equals to 0. Then you can get that the bending moment m is equal to minus 12 times 6 minus x squared. So as expected, this is a second degree parabola, and you can check that the concavity is downward here, also from this expression. So now, whatever you use, section or area method, you will draw your shear bending moment diagram. And because, as we discussed together here, we want to calculate the maximum normal stress, and we know that sigma is equal to m maximum times c over I. Okay, and because we don't have c1, c2, c1 equals to c2 here, since as we discussed, you have a symmetrical shape. Okay, so no need to differentiate between several cases. You only have to select the absolute value of the maximum bending moment. Okay, the absolute, because sigma is equal to m over s. Okay, and then sigma is maximum for the maximum bending moment in absolute value. The maximum bending moment in absolute value is 56. So now, to calculate sigma max, I just need to find what is the modulus modulus coefficient s of my section. Then I should go to appendix C. Why? Because in this problem, they told me that the beam I'm using is a NAS 250 times 52. So I will go to appendix C now to get the characteristics required. Here I just need to find what is the modulus S of this section. So let us go to the appendix together. From the appendix, you go first to S shapes. Okay, and in S shapes, you search for your beam. So it's S250 times 52. It is here. And you can read the modulus S directly, because as you can see here, if you go upward, this column is S of X. So here you are interested into S about this axis, okay? Because here this is your neutral axis, just at the middle. As we discussed, C1 equals to C2. So the table will directly give you the modulus S about x-axis. So you can say that if I go down now to my beam, the value of S is 452. Okay, it's 482, sorry. So this is the value desired. This is your modulus of your section, 482. And concerning unit, as you can see here, it's the value of Sx is times 10 to the power 3 millimeter cube. Okay, so the value in the table represents the value of Sx times 10 to the power 3. This is why whenever you want to find the value of S, don't forget to multiply by 10 to the power 3. So here you have 482 times 10 to the power 3 millimeter cube. And as we discussed, the maximum moment in absolute value is 56 kilonewton meter. You can convert it to Newton meter by multiplying by 10 to the power 3. And don't forget for your units to convert from millimeter cube to meter cube for us. So you just have to multiply by 10 to the power minus 9. And then the value of sigma you get will be in Pascal. So this is the maximum normal stress to which your beam is subjected. And since it's 10 to the power 6 Pascal, then you can say that the maximum normal stress is 116.2 megapascal. Now, let us do a design problem. So in general, in design problems, you have a certain unknown, and you want to find its value to not exceed the maximum allowable values. Okay. So for example, here we have, knowing that P equals Q equals to 480 Newton, determine the distance A for which the absolute value of the bending moment in the beam is as small as possible, and the corresponding maximum normal stress due to bending. Okay, so first, in general, when you have a load, you try to reduce the possible bending moment. Okay, so let us say here we want to find what is the best location of the roller D in order to have a minimum maximum value of the bending moment. Okay, so the idea is the following: we have a beam. We know that it's subjected to forces P and Q at points C and B, and we want to design a certain location of the roller from the pin A. So at A you have a pin, you have a YA axis. You want to design what is the most appropriate location of the roller in a way to reduce the maximum bending moment to which your beam is subject. Okay, so first, since A is an unknown parameter, we'll draw then the shear and bending moment diagrams function of A, and we can find then, if you want, the positions of maximum bending moment. We'll express these moments function of A, and then we'll deduce how A will affect the bending moment at extreme points. Okay, so the strategy will be first to draw the bending moment diagram function of A. To do this, first I find the reactions function of A. So all I have to do is to, for example, to get a Y, I do sum of moments about D equals to 0. As you can see, A reaction at A will be found function of small a. Now, in order to draw my moment diagram, okay, here it's very simple. Why? Because you have, if you draw your shear, you have always constant shear values. If I draw shear, my shear diagram will start by AY. Okay, so I have first AY, and AY here depends on the value of A, of course. But if we want to just draw the profile, okay, we have that from A to C, we have the value of the shear is equal to plus AY. Now, under the effect of load P, the shear will drop, okay? So the shear will drop downward because P is a concentrated force downward, and this distance will be equal to 480. And you know, as you can see in this figure, A is larger than 0.5 meters. So we want to place D somewhere between C and B, okay? So for A larger than 0.5 meters, if you replace here, you will see that the reaction at A is smaller than 480, okay? So of course, after the jump down, the downward jump of 480, we'll get a negative value of the shear. Now the shear will remain constant until D. At D, you have an upward reaction, dy. So this will cause now, if you want, an increase in a sudden jump in your shear diagram. Okay, and then after D, from D to B, you don't have any change. Okay, and at the end, at Q, you have a downward jump of 480 to 0. So here's the value at this level should be 480, because once you reach B, okay, Q, the downward force, will bring you back to 0. So this is your diagram. This is your diagram of shear. From your diagram of shear, you can deduce your diagram of moment. So you have first, from A to C, a positive shear. So a positive constant shear. So you have a linear increase in M. From C to D, you have a negative shear. So you have a downward, you have a linear decrease, and it's a linear variation because V is constant. And finally, in the final stage, you have your V is equal to 480, which is a constant. So the slope from D to B is equal to 480. Okay, so here phi is equal to 480, and this will bring you back to 0 because at the extremity there is no couple, so the bending moment should be 0. So if you look at your figure now for a bending moment, your bending moment, as expected, starts by 0 at A, which is the extremity, and ends at 0, which at B, which is the second extremity, because you don't have any couple at the extremities or fixity reaction. So, and we have two extreme points, C and D. You have the maximum bending moment at C and the minimum bending moment at D. Okay. Now, when we talk about the absolute value of bending moment maximum, then we should compare the maximum and the minimum. Okay. And let us find together expression of the maximum positive moment here and the maximum negative moment here. So to get the value of the moment at C, we can just do a cut at C. So if you do a section at C, you can get the expression of the bending moment at C. Okay. To get the bending moment at C, you have this is AY. When you do the cut, the section at C, you have that this is M of C. And you have the distance from A to C is 0.5 meters. So you can just write that doing the analysis on this part, we have sum of moments about C equals to 0. So this is the section part. Here we just do the section at C, at the point of interest. We are not finding function of X because we are just interested at the value of bending moment at C. So we do the cut at C and we do sum of moments about C equals to 0. We get minus 0.5A plus MC equals to 0. And we replace A, the reaction big A, by its function of small a. And as you can observe here, as A will increase, the bending moment at C will decrease. Will increase. Why? Because when A will increase, this term will decrease. But since you have a minus here, then this term will be larger. So the bending moment at C will increase with an increase of A. Okay. Now we will demonstrate that the bending moment at D will decrease with A. And therefore, when A, if you want, is increasing or decreasing, this will favor the increase of one bending moment compared to the other. And then the minimum possible maximum value will be when MC is equal to MD. Okay, so I repeat the idea. You have A is varying. A is varying in a certain range. A is varying between, so as we discussed, A should vary from C to B. So it should be larger than 0.5. So A is between 0.5 and 1. Okay. Now, we'll see together that A will affect the values of the maximum and minimum bending moments. Okay. It will lead to the increase of one in absolute value and the decrease of one of the other. So if you take the extreme of A, if you take A very close to 0.5, you will have then the bending moment at point D, because look, we until now we have calculated M at C. Okay, we can see that from the expression of M at C that increasing A is in our favor. It will increase MC, because larger is A, smaller will be this term, and larger will be MC. So increasing A will tend to increase MC a lot. So as you take A closer to 1, you will get a very large value of MC, so a very high positive maximum moment. On the other hand, if you do the analysis on bending moment at D, then you will do the cut at D and find the value of MD. You will get the following. First, let us go back to the figure. If we do a cut here, the easier part to keep is the right part. And when you take the right part, the convention of bending moment is clockwise to compress the upper part.